Okay, thank you very much, and I will be speaking about Bayesian approach to inverse problems. So I would like to define my setting first. So I am interested in the situation that I would like to find some information about a function or parameter u, and what I have at hand is some indirect measurements of u only via a function g, right? Now I will be assuming that this g is well posed, right? However, since these are only measurements, they can be erroneous. There might be noise involved, so y might not lie in the range of g. So I might have that problem that I cannot invert it for that reason. And also g minus, even if y lies there, g minus 1 might be very complicated and it might not be inverse. The inverse of g itself is not well posed. It might not be well posed. Okay, so a couple of examples. So this is the inverse heat equation. So what I'm measuring is the temperature distribution at the unit time, a later time, which I have fixed at the unit time. And what I'm interested in is finding the initial condition of the heat problem. Now this is a one-dimensional space, an interval, so I have explicit solutions, and I know that if I have a Fourier expansion of the initial data, then I will have the solution of u at any later time. Now, of course, this is heat equation. The solution at any later time is infinitely many times smooth. But even if my measurements are smooth, I can be in a situation that I lack stability. So, for example, if I am measuring, in an ideal world, I'm measuring the whole temperature distribution, I have error, but the error is at a very high harmonic, like sine 100x, and with a small alpha, the error is not very big. But then because of the way that you see these coefficients get multiplied by a very small one when you are going at a later time, therefore when you are going back in time, you do the reverse, so the initial condition, which is the quantity that I would like to find, that gets multiplied by this huge number, right? So small changes in my data are going to give me very big changes in the quantity of interest, so I have lack of stability. Another example is this famous elliptic PDE that we have seen a lot for the surface flow, and the situation that I can consider is the situation that I am measuring the pressure field, the solution of the forward elliptic PDE at some points in my domain, and what I'm interested in is the permeability coefficient. Right? Now, it's good to notice that this G is now, of course, P composed with the observation operator. So when I talk about this curly G, I am talking about something that involves both the forward model of the PDE and the observation operator. That is what I call G, of course. Now, in this situation, the forward operator, the operator that maps U to solution P, is nonlinear, right? And therefore, this curly G of mine will be also a nonlinear operator in U. So I am not excluding the situation that my forward operator is nonlinear. Okay, so we have an ill-posed problem. We have erroneous data, but nevertheless, we would like to find at least a reasonable estimate of this quantity of interest, which is U. Okay, so the most natural thing that comes to mind is that, so how about finding the u which minimizes the distance between my data and g? That's the most natural thing that comes to mind. But then this thing, if you have x an infinite dimensional space, you might end up with minimizing sequence which does not converge in x, right? So to make up for that, then you add some regularization term. So you add this function of uj, which is typically convex, something like that, and then you minimize this. This is what they do in classical regularization, and they end up finding one single estimate for u. Or what you can do is, applying a Bayesian approach, you suppose all variables involved in your problem are random variables. Okay, so this is my problem again. I am making erroneous measurements of g of u, so that error I have, I am supposing it's defined, it can be expressed by additive noise, right? So that I am fixing my setup like that. And then I am supposing that y, u, and eta, all of them are random variables. Okay? Now the general setting I'm going to consider is that my u lives in some space x, which is in general a function space. I suppose it's a separable Banach space. My y are the vector of observation, so I suppose it's a finite vector living in Rj. And then the prior beliefs, prior to measurements, I express in form of a prior measure, which I call mu naught. And then I suppose that the statistics of noise is known, so it has a density rho eta. So I'm going to apply Bayes' rule. So I would like to express, to update my prior, my initial information using this data that I'm gathering, okay, using Bayes' rule. Right, now when x is infinite dimensional, of course, as we have seen repeatedly in this conference, implementation of Bayesian approach requires high dimensional discretization. And then an important question to answer is that, does this discretization scale well with respect to refining the discretization, right? So there are two approaches, two body of work to address these. One is the discretization invariance theory, which says that, well, first take this inverse problem that's coming from your PDE and discretize it. And you will have a finite dimensional problem. Apply your Bayes rule to your finite dimensional problem. You get a mu posterior measure on this finite dimensional space. Then look how it behaves as you are making your discretization finer and finer. So if it approaches to something sensible, then you say it's discretization invariant. If not, then there's a problem. So one is a body of work originated by these guys and a lot of other works that I haven't mentioned here in this area. And then there is another approach which says, okay, so don't do the discretization first. First try to define your measure on this infinite dimensional setup, and then establish its well-posedness, and then see how it discretizes, if you want, how the discretization of the forward problem affects now this entity that you have found, which is well defined. Okay, and this is based on ideas by Andrew Stewart, and it's this nice review paper in 2010 which explains it. So I'm going to concentrate on this and some work related to it, and explaining, reviewing what has happened in this way of thinking. So of course the mathematics for this second way is more involved, but then it gives rise to a nice mathematical setup. Then, as I said, you can talk about the well-posedness with respect to changes in data, and also how the approximation affect the posterior. Okay, so that's what I'm going to tell you about that second body of work, the well-posedness of the posterior. I will talk a little bit about the approximation, finite dimensional approximation, and then the consistency of the posterior measure. Okay, so let me just remind you of the setup that I have. So that's my forward operator, indirect measurement, and noise eta. Prior is mu naught, and the statistics of noise is expressed by this density rho eta. So I hope to apply the Bayes rule. Well, I have the prior, I need the probability of data given u. So if u is fixed and I know the statistics of eta, then the density of y is just the same, except that it's translated by g of u. Right? So I know the probability of y with respect to u. And if I am in the infinite dimensional setup, what I hope for, since I don't have any density, is finding the Radon-Nikodym derivative of posterior with respect to the prior. So this is just the Bayes rule written in terms of the Radon-Nikodym derivative. So when well defined, it should satisfy a relationship like that. Okay, so that's just the same relation, the last relation in the last slide. I have just rearranged it. So in the left-hand side, we have the Radon-Nikodym derivative, and this is the likelihood. And just for convenience, this function I'm going to write as the exponential of minus phi. So phi is negative log likelihood, just for convenience. Now, the density rho eta, I suppose, is just a notation. I suppose it's the density of the measure Q on my space Rj, the space of data. And remember that X was a separable Banach space. And the result is the following. So as you expect, if you want this Radon-Nikodym derivative to make sense, you want the right-hand side to be measurable in both u and y. That is what this relationship is saying. So phi is measurable in both u and y with respect to the information that I have prior to measurement, which is the prior and then the product measure that is formed by the prior and this q, which corresponds to the density of the noise. And then, of course, I am after a probability measure. I would like to normalize, so I want my normalizing factor. So this is just the normalizing factor of the right-hand side with respect to the reference measure mu naught. I want this to be finite, so that's also a natural condition to have. And then if you have these conditions, then you can show that the posterior measure is well defined and absolutely continuous with respect to the prior. Okay, and then so I have the well-definedness. We would like to know now. We would like to know now if the changes in data. So we have some sort of well-posedness. We would like to know that the small changes in data result in small changes in the measures, right? So the measures are defined in this space X. I need a metric to be able to talk about their distance. The metric that I choose is this Hellinger metric, defined with respect to a reference measure, which is irrelevant. It doesn't matter which reference measure you choose. So conveniently, of course, you can choose your mu naught prior measure here. So you can choose anything for mu. And then, of course, as soon as you have your phi to be Lipschitz in your data with an appropriately nice coefficient, Lipschitz coefficient, so the only condition is that it is integrable with respect to the prior measure, then you have the stability. You have the distance between the corresponding measures to these two data points remain close if the two data are close, and the relationship is linear. No, the bound is linear. Okay, so I would like to write this down to remind you about the expression of so remember that right, so that's where this phi appears, and this was related to the statistics of the noise. So for a Gaussian noise, okay, phi would be something like that. If this is the covariance matrix of your noise, it would be something like that. So having phi Lipschitz continuous in Y is not very difficult, at least in that situation, to establish. Okay, so we have the stability. And then one remark about the Hellinger metric. The Hellinger metric is convenient because then the expectation of different functions of u under mu and mu prime are bounded linearly like this in terms of Hellinger metric. So it's a convenient choice. Right? And usually what you are interested to calculate, as we have seen repeatedly in the previous talks, when you find the posterior, you are after expectations of different functions of your unknown under the posterior. That's what you are interested. So these are quantities of interest usually. Okay, now I will talk about the approximation of the posterior, but before that I would like to tell you about how we construct the prior in such situations. Okay, so I have a separable, if you remember, I have a separable Banach space as the space that my unknown is living in, and I'm going to consider its basis to be this psi j, okay, the basis of this separable Banach space. And then I'm going to define my prior measure using the Karunen law of expansion of the draws of mu naught, right? So I'm going to say that I define random functions u using this series. So this is basically like a Fourier series. So these are the members of the basis, right? Generalized Fourier series, and then times a coefficient, alpha j k psi j. Now this coefficient, to get random function, I randomize this coefficient to my purpose. Okay? So my k psi j are IID random variables, and then alpha j are just numbers, decreasing sequence of real numbers, and cooked in a way that I get the smoothness that I like for u. Okay, so I want my u to live in X, so I choose alpha j so that that smoothness is produced for you. Okay, so examples are the Gaussian one. So if you want to construct a Gaussian measure on X, you do the same thing. Let's say on L2, you take a Fourier basis. K psi j are the 1D Gaussian densities, and then alpha j are is a decreasing sequence depending on which space you want to get. A generalization of that is the best of measures. So the way that they are generalized, you are this power 2 here, you are changing to q, okay? So if you have q equals 1, you have the exponential distribution, 1 the exponential distribution, and then psi j is an orthonormal wavelet basis, okay? So if you have that, then you have the so-called best of measures, which in this context, Bayesian approach to infinite dimensional problems, they were introduced by these guys in 2009 for the first time. And then for q equals 1 is especially interesting because it's the most sparsity promoting. Okay. So let me explain a little bit these best of measures before I move on. So these are based on wavelet expansions, and therefore they are appropriate for the situations that the function you want to find is a smooth function with few irregularities. So for example, in the subsurface flow, you heard that you can have different pieces of rocks with different permeabilities next to each other. So within each rock you have a smoothness, but at the interface you have irregularities. For such situation, of course, the wavelet expansions are more suitable. And then this L1 q equals 1 situation, this promotes a sparsity, right? And the reason is that you can think of it like that. Of course, there was also a mention of it in one of the talks before with a very nice picture, but you can also think about it like that. So if you have a sequence of real numbers like alpha j, then if you consider once the sum of alpha j themselves and once the sum of a squared of alpha j, and from both you want to get the same number, okay? So for this power 1, you want to have the farther away j's to decrease more quickly, okay, than this one. So that's why that you say it's a sparsity promoting. So this combined with the wavelet situation, which for such functions tend to give a sparse, such functions with few irregularities tend to give a sparse representations. Okay, so of course I said that in the context of Bayesian for infinite dimensions, they were introduced in 2009, but I should mention that the idea, of course, existed in the statistical literature for a long time, so, and appeared in works of Johnston, Donahoe, and Elad and others. This L1 combined with wavelet idea. And then, of course, this idea is central in compressed sensing, as we saw also before in the talks. Okay, so what I have so far, I have the well-posedness of the posterior. I know how to construct my prior, and I know the conditions on phi, which basically relates to my forward operator, as you can see here, that are giving me this well-posedness. So let us apply it to this problem of elliptic PDE, the subsurface flow. So remember that we are measuring P and we are interested in permeability coefficient. So I am considering the noise for each of these measurements to be Gaussian, and they are independent as well. So that's my phi, because eta j has Gaussian distribution. Now, X is the space my U lives in. So if you think about this permeability of rock, then what you expect, you want your X to be L infinity. No? So you have one permeability and then you are jumping to another rock with another permeability. So ideally you would like your X to be L infinity. And you want to construct your mu naught in a way that it charges the functions in L infinity with probability 1. Okay? So if you want to put a Gaussian measure, then if you choose the covariance operator of your Gaussian like this in terms of the negative power of Laplacian with S sufficiently large, then you're going to get the situation that your prior charges held their functions with probability 1. Okay, so you can choose your S as close as you like to d over 2, and you will have as small as arbitrarily a small CT. Okay? So you cannot go down to L infinity, of course, because L infinity is not separable, and using the way that we are constructing at the end of the day, we would also like to discretize. So you go to a little bit smoother space. With the Besov measure, again, you can cook up your Karunen law of expansion. So this psi j, remember, are exponential 1D exponential distributions, and then you choose this decreasing sequence to decrease fast enough so that you get the again Helder functions charged with probability 1. Okay. So this is how you construct your mu naught for this space that you have at hand. And then you want to make sure that your phi is measurable both in u and y. In y it's measurable easily because of the way that it's defined, through this continuous function. And then with respect to u, then you can show for this elliptic problem that you have at hand that you still have the Lipschitz continuity with respect to u, and therefore, in particular, you have measurability. Okay. So as soon as you have that, then phi is measurable with respect to this product measure, and therefore your posterior measure is well defined. Okay. So that's how it works. Is well posed as well. Okay, now going to finite dimensional, approximations first, and then in particular finite dimensional approximation. So now we are in a situation that we have approximated the forward operator. Okay, so phi depends on the forward operator through g. Okay, we have approximated the forward operator, and therefore we have an approximated minus log likelihood. Okay, phi n. And then now this new phi n has given rise to a new posterior measure mu n. Okay, so this is my original posterior measure corresponding to my problem, and this is the one coming from the approximated underlying PDE, let's say. Now, if the approximation in the forward operator is nice enough, so nice in a way that then phi minus phi n is decaying with respect to n, so this psi n goes to 0 as n goes to infinity, and then this coefficient is also nice enough in the sense that it is integrable with respect to mu naught, then mu and mu n, mu and the approximated mu, remain closed. Okay. The same approximation properties, so the same psi n carries over here under the Hellinger distance. Yeah. Okay. Now, so this is the previous one was for any approximation, and here we have the situation that you have some sort of a Galerkin finite dimensional approximation. Okay, so suppose that my X is a Hilbert space and I have a orthonormal basis psi j in it, and then consider W to be the span of the first n members of this basis, and define this orthogonal projection from X into W. Sorry, I have to write W, but then it's yes, I have to write W. It's an n-dimensional space, so Pn is the projection, the orthogonal projection from X to W. Now, define this phi n to be phi of Pn applied to u. Okay, so I am discretizing my u, my unknown. Okay, so I'm projecting it on w, and then I apply my forward operator to it, and then I get correspondingly an approximated phi. Okay, so remember this is phi over there. Okay, and I suppose that the situation is nice enough so that this is a good Galerkin approximation with psi n going to 0. Now, I'm going to construct the prior measure using the KL expansion that I get from the same basis psi j that I use for my approximation. Okay, so I construct my mu naught using the same psi j, and therefore in this setup the mu naught will be the product of two measures, mu naught n and this perpendicular measure to it, mu naught perp, yeah, which, well, the mu naught perp lives on the complement of w, no, direct complement of w in x. Okay, now this mu naught is going to give rise to a mu n, which will be also a product measure. So the measure on the complement of w will remain unchanged. The prior measure on the complement of w will remain unchanged, right? But the part of the prior measure on w will be changed, will be updated using the Bayes rule. So the posterior measure would have this product form, and this part, the nu n, which lives on w, yeah, satisfies this condition. It's Radon-Nikodym derivative with respect to the part of the mu naught living on w satisfies this relation. Okay. Now, as soon as you have that, then you can talk about comparing the expectations of different functions of u under mu and under this finite dimensional measure. Okay, so you have a well-posed measure on an infinite dimensional space. Practically, you need to look at a discretized finite dimensional version of it. So this is telling us how the expectation under this finite dimensional approximation and the expectation under that original true one compare, right? So we have seen talks on uncertainty quantification also for this elliptic problem, for example, that you have your the elliptic equation for the subsurface flow. This is random, right? And then you want to study how this randomness carries over the equation, okay, onto P. Now, what this is doing, it's saying, okay, so put some randomness on this, like a Gaussian measure, but then you are able to collect some data. So first, update this prior using your data. So from your mu naught, go to mu. Now you have an updated prior, which hopefully is better quantification of the uncertainty in u, no, because you have updated it with your prior. And now see what happens when you run this mu through your equation. Okay? So you can say that you are getting an improved quantification of uncertainty. Okay, so as an example, let's look at again the elliptic situation. So, right. I am considering the inverse problem. So what I want to do, I want to perform this this update now from mu naught to mu first before doing the uncertainty quantification, the weak uncertainty quantification. So supposing that I am in the situation of subsurface flow, a Bessov prior is more appropriate. I have chosen my mu naught to be a Bessov prior. And then with a wavelet basis, and I am considering the W, the finite dimensional subspace, to be the span of the first n wavelet basis. Then, well, I have updated my prior to mu, okay, and I'm interested in how the approximation of mu with a finite dimensional approximation of mu is going to affect, is going to show itself in the randomness in the solution of the PDE. So I can do that, and what I obtain is this, that the mean is going to, using an appropriate wavelet basis, is going to decay like this, and the variance similarly. So remember that I am putting a BS1 Bessov measure. S is bigger than D, and this T is the Helder space with exponent T comes from the Helder space with exponent T, which is less than S minus D. So if you remember the way that we constructed the prior measure for the elliptic problem, the T in the decay condition is the same T that you get here for the Helder space. Okay, so now I would like to talk a little bit about the posterior consistency. Yeah, so I'm going to assume the frequentist assumption that there is an underlying truth, and therefore my data are generated like that. So I am able to collect as much data as I like, so I am making my observation repeatedly, okay? N times, N as big as I like. G is similarly, as I have defined it before, it acts on a function space X, and these are the elements of the vectors lives in Rk. So now this leads to a Bayes setup like this if I choose the prior measure to be Gaussian. So the posterior, given all the data, has this Radon-Nikodym derivative with respect to mu naught. So in the left-hand side, you have the sum of yj minus g of u for all the data, j equals 1 to n. And you can obtain this by just stacking all these vectors together in one big vector. You will get the same. You will get this result. And now the question that I'm asking is the following. What happens as n increases? Does this posterior measure give better estimates of my truth as I'm increasing u? Does it concentrate around the truth as I'm gathering more and more data? So you expect that the posterior concentrates around its mode. That's what you hope for. So we are going to look at the most likely functions under the posterior. Okay, so if we were in finite dimensional situation, if X, the space that your unknown lives in, was finite dimensional, then things were very easy. So all of these things had densities. So if, for example, mu naught is a Gaussian with covariance metric C naught, then you're going to have the density of your posterior to be like that, this exponential function. And of course, if the mode, the most likely function of the most likely point of the posterior would be the minimizer of this functional here, this function here, right? And that's that. In the infinite dimensional situation, you don't have densities for mu and your mu naught. So the way that you can talk about most likely functions is using these little balls that you move in your space. So you have your space X, you take a ball of fixed radius and you move it in your space, and for each fixed radius you find the center of the ball which has highest probability. Okay? And then you look at the limit of these centers as you are shrinking the radius of the ball. Okay, so to be more precise, so this is the ball of fixed radius delta. You are moving it to the inside the space, and you are finding the one with the maximum probability. You call it Z delta, right? And then you are going to look at this limit as delta goes to 0. Okay? So the point Z delta which satisfies this relationship is going to be your mode. Right? So this is what we call map estimator, or a strong map estimator, after people come up with a very useful, nice other notion called weak map estimator, which I'm not going to talk about today. Now, with that definition, then you have what you expect. Yeah? It's not very surprising that the map estimators are characterized, the modes of the posterior are characterized by minimizers of this functional, right? So in the infinite dimensional space, if you just formally, of course there is no density, but if you only formally suppose that your mu naught has such a density, e to the power of -1/2 u e squared. So this e is the space of admissible shifts, no? This is almost everywhere infinite when you have infinite dimensional space, because it's much smoother than the space X itself. But if you assume just formally that it has such a density, then this form is exactly what you expect to get, and that is what you also obtain, that the map estimators or modes of the posterior are minimizers of this functional. Okay, so this is for such analysis you need to every time fix your mu naught, because this function here depends on the type of the measure that you are taking, and this is true also in the case of the Bessel's. Also, it's good to notice that this is a nice relationship. If you look at this is exactly the form. Look at the form of phi. This is exactly the form that you get in the Tikhonov regularization. So this Bayesian approach over infinite dimensional space gives a nice link also between the Tikhonov classical regularization and the Bayesian regularization. Okay, and then we have this weak consistency that I was trying to find. So we want to see, as n increases, if this posterior, the mode of the posterior converges to the true solution, and the answer is yes under some conditions. So if your phi is Lipschitz and bounded below, you would have this result, right? So if your truth lives in your Cameron-Martin space, then you can find a U star for which you have the convergence of UN to U star, and this U star satisfies G of U star equals G of U truth. So remember, in general, my G is nonlinear So I cannot hope to have U star equals U dagger in the general nonlinear case, but of course this result says that if you have a linear operator, U star will be equal to U dagger. Okay? So this is a weak consistency result because I'm only talking about convergence of the mode. It's good to mention a body of work that people have considered the contraction rates of the posterior a stronger result. So you want to know that your posterior is contracting fast enough to the mode as well. In the conjugate Gaussian case, of course, everything is explicit and everything is well understood. The non-Gaussian case is more difficult and being developed at the moment. But for the nonlinear case, as one expects, there are only very partial results, as I have cited here. And that's all. Thank you very much.
Questions? Be brave. I'm going to be brave.
I had a question about choices of prior. So if I understood, you have theoretical conditions that tell you if you choose the prior in the right way, then you get your bounds for the error that you make in sort of approximation of the posterior. And you had two classes of priors that satisfy the conditions that you needed. And just if you bring that back to sort of what people do in practice computationally, often make quite a lot of crimes in the way that we choose our priors or construct our priors. So often something that people do is they take a Cohen-Lev expansion like you wrote out, but they might not choose the phi's the way that you did, and they might stick in, let's say, uniform random variables instead of Gaussian ones.
If you have also uniform, but for uniform random variables, again, if you choose those, so this was the Cohen-Lev expansion. Yeah, so you are saying that people consider this to be uniform.
Yeah, just because maybe our codes do that,
yeah,
or because they're simpler.
So I think you can work with uniform, and you can then choose alpha j to go to 0 fast enough to get something sensible. Yeah.
Okay.
So
my question is just, can something go wrong that we're not aware of?
Yeah, no, I don't think so. Depending on what you want to find, I don't think that would necessarily give, make things wrong. Yeah.
Can I say something about that? Maybe because if you do that and you want a positivity assumption on the coefficient, which of course would make sense for the elliptic problem, then you have to have a very strong decay, and that would basically give you a strong bias towards the first few psi j. So that seems to be the kind of experience there, that the solution basically looks like the first psi j more or less.
Yes.
So, got the kind of following question. So, what you're doing is basically infinite dimensional and then discretized, if I understand it correctly.
Yes. Yeah.
The other way that people often think more classically about it would be discretized and then Bayes. Can you say something about when you'll get the same posteriors in those two cases? Because they don't necessarily give the same answers.
Right, so for example, if the discretization is done, for example, using one of these Gaussian,
right?
One of these Galerkin things I was talking about, of course you would get the same answer, right?
If you use a Gaussian prior.
Yes, or Bessel, or anything that that you can show that is discretization invariant in the language.
Okay, that makes sense.
So that makes sense. But there are other ones that you don't get, and so they might not be discretization invariant. For example, the TV prior is not. The TV regularization, the one that comes from TV, wouldn't be discretization.
Which also is kind of intuitively makes sense, I think.
Yes. Yeah. Right.
Okay.
Yeah. That's so. But you might find it still useful in finite dimensional situation to do. So I don't know. I cannot comment on what would be the.
Well, and that's where it gets a little tricky, because a lot of these may be useful if you do the discretized then Bayes, but you may get quite different answers, and yet it may be useful. And it's a funny thing mathematically to try and resolve that.
Right. Yeah. Yeah. So what comes to my mind is that, of course, for each of these, you need to choose a particular prior. Right, to start with this infinite dimensional setup.
That is consistent with that, yes.
That is consistent with that. So maybe in your situation, one of these priors that are very useful, we haven't yet constructed such a thing. So, yeah.
And that's exactly the case, because often we'll just say if we don't know anything, we're going with a flat prior, when we're going finite dimensional, yet that doesn't work so well for the infinite dimensional, is my understanding.
Right.
Yeah, and so that's exactly one of those cases.
Yeah, this is what Catherine was saying.
Oh, okay. I'm afraid I couldn't hear the question so well back here.
Was that related to? No. Okay.
I'd like to ask, hand up. So, what is the sampling scheme? You've got these y's that you're observing, yeah?
Yes.
And you've got an n that goes to infinity.
Yes.
Okay, so, what is the scheme? Are you allowed? At one point, I think you said you're allowed to replicate. Have you got repeated realizations? But where are you taking your sample?
Actually, I haven't talked at all about sampling.
But in some sense, you have to talk about sampling. If you're going to have a consistency result, you have to tell us what the sampling scheme is.
You mean where she has her observations?
Where the observations are, yeah.
Right.
Because that should be contained in the. Sorry.
Right.
Are you repeating at the same location at the time? I mean, I don't understand.
Yeah. So these are the points of observation. So, for
Yes.
example, in the situation, so I am not. So you mean about you mean sampling the observation, or you're talking about sampling from measure? So maybe.
With your data, where is your data?
Yes. Yeah. So, for example, in the case of the elliptic situation. You are measuring the pressure, at some points.
Yes.
So the only thing I was saying is that suppose that you can do that measurement as many times.
As many times. So
as
that's
you
what
like.
we call replication.
That's correct. Yeah.
Thank you.
Yeah.
Sorry, you were just in front.
Just going to follow up on that point, Meg, on the point that Masoumeh made about the sampling from the posterior measure. So in the discrete parameter case, in a non-linear function, you have to use, MCMC or what have you to get your posterior. You didn't really talk about how you would do that here.
No. So you said if what was your question?
Well, so in the discrete parameter case,
yes.
Yeah, I know how to do MCMC, for example, to sample from the posterior distribution parameters.
Yes.
What's the analog in the infinite dimension?
So, well, I am far from an expert in that, but so you have this Radon-Nikodym derivative and mu y in terms of mu naught, so you can take it from there and then construct some sampling schemes based on this Radon-Nikodym derivative that you are getting from there, but at the end of the day, you need to discretize again. That is how I understand it. Yeah.
Okay.
Yeah. So this question would concern what the stability that you get actually depends on, because the Lipschitz continuity of the phi that certainly comes in, right? So that would also depend on the variance of the noise. So if the variance of the noise goes to zero, which classically would be called as noise level, then somehow this Lipschitz constant would go to infinity, right? So somehow the stability would somehow deteriorate if you have less noise. Is that correct?
Right. Okay, so let me think. Let me show you the place that we have that n data, because then you can divide by n. It would be similar, no? So let me have a look at that.
There's an n in all of this.
Sorry. Okay, so you can say the other way around, that if as n is increasing, this is becoming an infinite sum, and no, that's so for any finite n. So of course, my n is going to be finite. I'm only interested in. So the way that if you look at here, the way that we are dealing with it, you see. You end up with such a thing. So if you had the noise, then you would get some 1 over gamma squared perhaps here, right? And then you are looking at the arg mean. So, well, mathematically, it wouldn't make any difference if I multiplied everything. Also with gamma squared. So that's how, in the process, somehow we get rid of that n. In here, so I think it's similar.
But the second term dominates, you're saying? That term dominates?
That's right, yeah. So let me see. That's right, exactly. And then when you divide by n, then you are saying that the effect of this term is becoming smaller and smaller. That's what you're saying.
That's why we need to. Yes, Peter.
As far as I understand it, you've got no model discrepancy in here, your model and the data. Could you expand it to include a model discrepancy?
Well, theoretically, I think yes, because then you can think of it as a parameter inside your original model and then put a prior on it. Right?
Okay, but there are identifiability problems which Tony raised. I just wonder whether you can have those same problems.
I don't know what you mean by that.
So I'm balancing how you modify the values of u to get close to the data, compared to including this discrepancy, this difference between the data and the values coming from the model.
Mm-hmm.
Which may kill the consistency, right? They
Yeah.
Right.
Right?
Shorted.
Right, so what you're saying is that so I am considering something like that now, assuming that my model is nice. Yeah. So now what you're saying is that I might have another term, call it alpha, that might
Delta, I think.
We can handle alpha.
Yeah, so, yes. So why can't I consider both of these as the unknown of my system and put priors on them?
Yeah, but the thing is, you can't uniquely find u then, because you have to estimate u and delta.
That's right, but then
u
delta is going to be in x times z, and then I am finding them together. What does stop me to do that?
So the thing is that you find the summation, you find the sum of g of u. You find a solution for g of u plus delta, but you don't know how what delta is and what g of u is.
It's like two people standing on the weighing scale at the same time.
Exactly. Yeah. And so this last condition is not guaranteed. That's I think what last condition on your slide there. That you find that your u star will be equal to the real u. You can't say much about it because there's delta floating around.
Oh, you mean here?
Yeah.
That's right. Okay, thank you.
Yeah.
Yes, that's right. Okay.
I think it's been a fantastic talk. I think we should stop and say thank you
Thank you very much.